Okay class, so today we'll be discussing practical application of refraction. So what is the first question? Why is the apparent depth of an object placed in a denser medium less than the real depth? Okay, so before we analyze this question, I will just introduce with two new concepts. The first concept is known as my principle of reversibility of light. So before we go into this topic, we will first understand your principle of reversibility of light. Now in this topic, what happens? Suppose you have two mediums, your air and your water medium. We know your air is what kind of medium? It is your rare medium. What is your water? Water is your dense medium. So a light is going from your air to water. This is the light which is going from your air to the water. So this light makes an angle I with the normal, and after refraction when it comes out, it makes R with your normal. Clear? So since our light is going to water from air, so how do we write down? Mu, which is your refractive index mu water to air, or water with respect to air, equals to sine of I divided by sine of R. Clear? Okay, now the light has gone from air to water. Now what happens if I put a mirror? If I put this mirror, this light will again go back along the same path. So when I will put a mirror, this light goes back along the same path, but this time my light is going from water to air. So how will I write my refractive index? In which medium it is going? Air. From which medium? Water. So mu A W. But remember, this time what is your angle of incidence? It is your R, because see, this is the incident ray. So this is my R, and this is my refracted ray, so this is my I. So refractive index of air, mu of air, it is going to air, so I'll write down air first, then water. Refractive index of air with respect to water. Now in this case, which is my incident angle? Is it I? No, it is R. So I'll write down sine of R. And which is my refracted angle? It is I. So I'll write down sine of I. So don't get confused. In this case, light is coming in this direction, and in this case it is going in this direction. So use your logic. In this case, this is my incident angle. For the first case, this I is my incident angle. Clear? They are the opposite case of each other. Now we know refractive index of water with respect to air is sine I by sine R. Water with respect to air is sine I by sine R. Now we know a property. If there is a number or fraction written as A by B, I can also write it as B by A, where I have taken this A to the denominator. So sine I by sine R, using this property, I can write 1 by sine of R divided by sine of I. Now you know what is sine of R divided by sine of I. It will be refractive index of air with respect to water. So instead of whole thing, I can write refractive index of air with respect to water. Is it clear? So refractive index of water with respect to air equals to 1 by refractive index of air with respect to water. Or I can also write refractive index of air with respect to water equals to refractive index of water with respect to air. So this is your principle of reversibility of light. Clear? Okay, now for your second concept, you have to remember, like I have already told, whenever a light passes from water to air. What is your water? Water is your dense medium. What about air? Air, it is a rare medium. Whenever a light passes from denser medium to a rarer medium, what happens? Suppose this is my denser medium, okay? The light is going in this direction. What happens after refraction? What will happen to the light? It will bend away from the normal. If the light is going like this, after it passes to the second medium, it will bend away from the normal. So in this case, my light will be bending away from the normal. Now the other one is that whenever your light, okay, is passing through the normal, okay, we don't consider any refraction in this case. In this case, angle of incidence equals to angle of refraction 0, which is my ideal case, okay. On the basis of these two concepts, we will go to our next topic, which is your practical applications of refraction. Okay. On the basis of the previous two concepts, we will try to derive the practical applications of the refraction of light. Okay. Now let us consider we have a water beaker. This beaker is filled with water. Let us consider an object. This O is my object which is placed at the bottom of the tank. Okay. Now there are two rays coming out of this O. This is my first ray. This is my second ray. Clear? These are my two rays. Let us say this first ray is my OA. The second ray is my OB. Okay. So since both of these rays, what happens? They undergoes refraction. Now this ray is passing through the normal, and we know whenever light passes through the normal, it passes undeviated. So this is an ideal case. What about in this case? In this case, what happens? It is passing from a denser to a rarer medium. So what will happen? It will bend away from the normal. It will move away from the normal. Clear? This is my angle of refraction. So this is my third ray OBC, and this is my first ray OAD. Clear? Now imagine if you are looking through point C. If you are viewing from the point C, what will appear? It will appear that the object is somewhere here. Okay. It will appear that you are watching the object at this point. Okay, not here. Because whenever we see a light, we see it in a straight line. So for us, it will appear that the object is at this point. So this distance, okay. So this distance, what do we call this distance? This is my apparent distance. Apparently this is the distance which we see, but what is my actual distance? What is my actual depth? OA. This is my real depth. Yeah, this is my real depth. Okay. Now based on some properties of the triangles and triangles, okay, now we know whenever we have a triangle, okay, this angle is equals to this angle. On the basis of that property, suppose this is my angle R, so this angle will also equal to my R. Clear? Now consider two opposite. We have two opposite parallel lines. Whenever there's a line intersecting at it, this angle equals to this angle. Clear? What is this property? Vertically opposite angle. So in this case, this I will be equal to here. If there's any confusion, you can ask me in the comment section. Clear? Okay, now in your figure you can see that your point object O, this is your point object O. There are two rays starting from your point object O. This is your first ray. Now as I've already discussed, if the ray passes through the normal, it passes undeviated, so it will go in a straight line. So this is your first ray. Now for your second ray, this is my second ray. Clear? Now in this case, as I've discussed, whenever a light passes from a dense medium like your water to a rare medium like your air, what happens? The light bends away from the normal. Clear? So the light which is moving in this direction, after refraction will travel in this direction. Fine. Now for a normal human eye, what happens is that we see only the lights in a straight line. So what we will assume that this point is lies somewhere at this point I. For a normal human eye, he will see the straight line. So for him, this O will be somewhere at I. Is it clear? So now from your Snell's law, clear? Okay, before we go to the Snell's law, now can you see object O is at the end of your beaker or is at your bottom of the water tank. So if I ask you what is the real height or your actual height, what is the actual height? This is your actual height, which is the real depth of your water. Clear? But for the normal human eye, it appears that this depth is somewhere here. So what do we call this one? This is your apparent depth. Clear? Now clearly your apparent depth is lesser than your real depth. So now we will show this using our derivation. Now coming to our derivation from Snell's law. We know from Snell's law, as our light is moving to which medium? Air. From which medium? Water. So I'll write down refractive index of air with respect to water equals to sine of I divided by sine of R. Sine of I divided by sine of R. Now which is your sine of I? It is your A. Your sine of angle of incidence is just a moment. Okay, before we go to the Snell's law, now can you see object O is at the end of your beaker or is at your bottom of the water tank. So if I ask you what is the real height or your actual height, what is the actual height? This is your actual height, which is the real depth of your water. Clear? But for the normal human eye, it appears that this depth is somewhere here. So what do we call this one? This is your apparent depth. Clear? Now clearly your apparent depth is lesser than your real depth. So now we will show this using our derivation. Now coming to our derivation from Snell's law. We know from Snell's law, as our light is moving to which medium? Air. From which medium? Water. So I'll write down refractive index of air with respect to water equals to sine of I divided by sine of R. Sine of I divided by sine of R. Now which is your sine of I? It is your A. Your sine of angle of incidence is just a moment. Your sine of angle of incidence, it is AOB. So I've written sine of AOB. Now which is your sine of R? That is your angle of refraction, AIB. So I'll write down sine of AIB. Now consider your triangle AOB. We know what is the sine? Sine means your opposite side divided by hypotenuse. What is the opposite side? AB. What is the hypotenuse? BO. Clear? So I have written AB divided by BO. Similarly, consider your other triangle AIB. In this case also, which is your opposite side? AB. Which is your hypotenuse? BI. So sine of AIB can be written as AB divided by BI. Now I can write this one as AB divided by BO into This AB will be at the denominator and BI will go to the numerator BI. What happens? Your AB gets cancelled, and what you are left with? BI by BO. So I'll write down BI by BO. Now, pay attention carefully. Since your human eye is small, clear? Your human eye is small, and which is generally we are looking at the point C to see the light which is coming out of D. Okay, what do we have to do? We have to make these 2 points very close to each other. Clear? So what we are doing is we will try to put this point, your A and B, as close to each other so that they can be viewed by your normal human eye. So as the size of the pupil is small, the ray BC will enter the eye only if B is close to A. Now what happens if B is close to A? So this distance, which is your AI, this will be approximately equals to BI. Clear? So I've written BI approximately equals to AI. Also your distance BO, this whole length BO is also approximately equals to AO. BO is approximately equals to AO. If there is any confusion with this one, ask me. Clear? So your refractive index of air with respect to water. Refractive index of air with respect to water is BI by BO. So I've written BI by BO. And as I've already said, BI is approximately equals to AI. So instead of BI, I'll write AI. And BO approximately AO. So BO equals to AO. So refractive index of air with respect to water, I can write AI divided by AO. I can write it as AI divided by AO. Clear? Now, since for you who are viewing this thing, are you looking at from the water? No, you are looking at from where? You are looking at from air to water. So in your case, what happens? The light should go from the air to the water medium. So how do you write your refractive index? Refractive index of which medium it is going? Water with respect to air. Clear? We won't use this one because we are not watching from the bottom of the tank, but we are watching from the top, that is from the air. So if it is in air, the light goes in this direction. So water to air will be written as refractive index to water to air. Using your principle of reversibility of light, I can write 1 divided by mu of AW. Clear? Now mu of AW means AI by AO. If it is AI by AO, I can send this AO to the numerator. So this can be written as AO by AI. Now what is your AO? AO, this is your AO, is your real depth. What is your AI? AI is your apparent depth. AO is your real depth, AI is your apparent depth. So I can say my refractive index equals to real depth divided by your apparent depth. Clear? So this is an important equation. If you have any confusion, you can ask me in the comment section. Now instead of this, I can send this apparent depth here and refractive index here. So I can write apparent depth equals to real depth by refractive index. Is it clear? Okay, now I'll introduce another concept. Now let us look at our first fraction. Okay, this is your number, this is your numerator, this is your denominator. In your first case, your denominator is how much? 2. Now 2 is greater than 1 or less than 1? It is greater than 1. If 2 is greater than 1, okay. Now tell me which number is bigger, your 1.5 or 3? 3 is bigger. Okay, let's take another example. Let us say 3 and 1. Again, check the denominator. Denominator is greater than 1 or less than 1? It is greater than 1. If it is greater than 1, what happens? Who is bigger, your number or your numerator? Your number 3 is given. Okay, this is an example you can analyze yourself. So I have given you 3 examples. In all this case, what do you notice in common? my denominator is greater than 1. Clear? Now let us consider the opposite case. When my denominator is less than 1. Let us say let us say 1 divided by 0.1. 1 divided by 0.1. In this case, how much you'll get? 10. Clear? Again, let's take one more example. 1 divided by 0.01. In this case, how much you'll get? 100. Fine. Now, in this case, what do you notice? When your denominator is less than 1. When your denominator is less than 1. Who is bigger? Number or your numerator? The number 10 is bigger. Similarly, for your second example, who is bigger? 1 or 100? 100 is bigger. So what I want you to do is pause the video for now and take a good look at this 5 example unless and until you get the proper idea. If that's it, then let's go to here. As I have derived, apparent depth equals to real depth divided by refractive index. Clear? Or I can say apparent depth equals to real depth by refractive index. Clear? I'll just use the short notations. Okay, now let us consider for our water. In case of water, how much is my refractive index? 1.33. If the refractive index of water is 1.33, so substitute it here. Apparent depth, real depth divided by 1.33. Now 1.33 is greater than 1 or less than 1? It is greater than 1. If it is greater than 1, then who will be bigger? Your number or your numerator? Who will be bigger? Your number or your numerator? Obviously, your real depth will be bigger than your apparent depth. Yeah? Real depth is bigger than apparent depth. Let's take one more example. For the crown glass, refractive index equals to 1.52. I'll write 1.52. Again, in this case, my denominator is greater than 1. If the denominator is greater than 1, who will be bigger? Apparent depth or your real depth? Real depth. Clear? And this is the third example for diamond. Analyze this one yourself. Who will be bigger? Real depth. Fine. So after you get this much idea, look here. As we know, okay, refractive index of most of the mediums are always greater than 1. Okay, any material you have, all the materials have refractive index greater than 1. But be specific. Okay, I'm not talking about vacuum. Vacuum has refractive index equals to 1. We are not discussing about vacuum. We are considering any physical material. Clear? And we have taken the 3 examples. In this case also you can see all the refractive index are greater than 1. If in all of such cases your refractive index is greater than 1, okay, so what idea do you get? Who will be bigger, your real depth or your apparent depth? Your real depth will be bigger. If real depth is bigger, can I write apparent depth is smaller than my real depth? Is it clear? So in the question we have to show that why our apparent depth is lesser than the real depth. Okay, if you have any confusion, you can ask me. Thank you, class.